Back YouTube community. This is Prithvi Trinath. In this video, we'll be concentrating on discrete Fourier transform and its implementation on Arduino. Let's get started. This is the outline of the presentation. We'll start with the basics of DFT, that is discrete Fourier transform, followed by computing pulse rate from a PPG signal using discrete Fourier transform. This would be followed by computing pulse rate from a PPG signal using autocorrelation function and verifying the results of discrete Fourier transform with that of autocorrelation function to be double sure that both are working in accordance with each other. And this would be followed by the analysis of the results. So getting started, the discrete Fourier transform transforms a sequence of n complex numbers, say x0, x1 till xn minus 1, into another sequence of complex numbers, which is defined by the definition is shown here. This is the formula. It can be further simplified or expanded using the Euler's identity into cos and sine components. Well, this formula is important because we can, in order to implement this, we consider xn as a vector and e power minus I into 2 pi n by into kn as another matrix, n cross n matrix, and we multiply them. So it is important that you understand this formula better so that it could help you realize how we are computing it using matrices. When I'm implementing this on Arduino, xn would be a vector or n cross 1 matrix, and this second term would be also a matrix which I'll be calling wn, which is Kaplan cross Kaplan matrix. Oh, as in Arduino, we don't have a library for complex numbers. We will be using a separate matrix for computing the real part and a separate matrix for computing the imaginary part. And finally, what we need is just the magnitude of this. So we will be squaring and adding each and every term in all the matrices. So hope it is clear. So while moving on, DFTs are extremely useful because they reveal periodicities in input data as well as the relative strengths or weights of each of the periodic components. This is one of the most important property of DFT. In general, DFT of a real sequence is a complex sequence of the same number of elements or of the same length. There is a minor difference between DFT and DTFT. DTFT gives me a continuous transformed waveform. That is, I'll get x of omega, which is continuous for omega between minus pi to pi. But in case of DFT, I would not be getting a continuous transform waveform. I would be sampling the continuous transform waveform that I get in DTFT. Why would I do this? It is simple. In order to reduce the computational burden on my microprocessor or microcontroller or any device, I do this. So fine. Let us bounce off to the Arduino implementation of DFT. So this is X as usual is our input signal. So Y is my W matrix. Y is my matrix for the real part as I have already shown here. Y is my matrix that I will be using to compute this part, and Z is the matrix that I will be using to compute this part. O and O1 are my temporary variables, and F is my final output. These are other variables that I will be requiring. So as you can see, I compute Y and Z. I would in this way. I'm just hard coding whatever is there here. Whatever is there here, I'm just coding this. It's a simple code. Cos of something and sine of something. This would compute my W matrix. So next what I will be doing is I will be multiplying this with the input signal. As you can see here, I'm multiplying Y with input signal and again adding this. I'm iterating this loop. The number of times I'm iterating this loop is equal to the number of elements. So thus I'd be completely multiplying every element with the input message signal in this matrix. This will be followed by squaring and adding the magnitude spectrum. At the end, I would be requiring the magnitude spectrum only. So I would be getting f of I will be storing my magnitude spectrum of my input signal. So let us see how this magnitude spectrum looks like. As you can see, there are two peaks here. Amplitude represents the weight of that peak. That is how prominent that peak is in this signal. So we can assume that this frequency components corresponding to these two indices are play a prominent role in this PPG signal. So let us move on. So we find the indices of those peaks, and from the index obtained from from the first peak, uh, we convert that index into frequency again and multiply it with 60 in order to get the beats per minute. That is what we do it here. Uh, I divided by 3 because the formula is uh, BPM equals 60 into 60 because we are doing it per minute into index into Fs, that is sampling frequency, divided by length. Here Fs is 25 and length is 75. So I divided by 3. So let us see uh, what is the BPM that we obtain here. That's the BPM obtained here is 70. So please make a note of this value. BPM obtained through DFT is 70. Let us check what is the BPM obtained using autocorrelation function. So this is the code for autocorrelation function that we have implemented in the previous week. I'm using the same code. I'm just changing the inputs, and let us check what is the BPM that I'll be getting here. So the BPM obtained using autocorrelation function is 71.43, which is almost equal to 70. So from this experiment, we can verify that even DFT is an effective way for computing the BPM along with autocorrelation function. So what we have done here is we have used only 75 samples. We can't exceed that and use 100 or 150 samples because there is a memory problem with Arduino tube. So what we would be doing is we would be using MATLAB and use 150 samples and compute DFT matrix for it and compute the pulse rate at the end. So this is the MATLAB code. This is the code for DFT matrix in MATLAB. MATLAB has complex numbers, so it is pretty simple to code it. As you can see, I have created a function named GPT. GPT is my name, DFT matrix. Initially, I put that as zeros. Initially, it is necessary because in order to optimize my code and increase the speed, I need to initially specify the size of my matrix. Matrix size is n cross n, which I know, so I'm initializing that to zeros. So this is the code. I'll be needing two for loops, and I'll be getting my two-dimensional W matrix in this format. So coming back to the main code, so my sampling rate here is 50 hertz. So my time would be, I'll be taking 3 seconds. So I have 150 samples, so that would be 3 seconds. Since I'm starting from 0, I'd be ending at 2.98. So y is my input of 150 samples, sampling rate is 50 hertz, n is length of y. I'll be computing DFT matrix using n, this n only, and finally multiplying my input signal with matrix, taking the absolute of it in order to get the magnitude. Finally, beats per minute is nothing but 60 into fs into k divided by the length. So let us look at the plot. So as you can see, this is my input signal. So, and this is the magnitude spectra of the input signal using discrete Fourier transform. And this here, the x-axis is index k, that I've converted it into 60 into fs into k divided by n, which gives me in frequency domain, and that too, it's not just per second, it is per minute. So the value of the peak that I've obtained here would be my BPM. As you can see, the peak value obtained here is 80. Since we have used for 150 samples, and there was slight change in the frequency here and there, so thus the frequency has increased from 70 to 80, and thus through this experiments, what we have seen is how we can use DFT matrix to analyze a signal, to know its prominent frequency components, and also for a PPG signal, how do we find the peak. Hope you have liked this video. Please like and subscribe to our channel to find more interesting videos. Thank you.